I'm Connor Frederick, a postdoc in Scott Didham's group at NIST in Boulder. And our collaborators are Ryan Sureth and others at Carleton College and Penn State. We know radial velocity measurements are correlated with stellar activity. So can this information contained within individual line shapes be used to correct for that activity? And how much information do we actually need to do that? This is where our Heterodyne spectrometer comes in, which allows us to explore this problem with a high resolution instrument that doesn't have the same systematic issues as traditional spectrographs. While this presentation is focused on the radiometer design and performance, for a look at where we are headed with this modeling, make sure to stop by Winter's poster. Laser heterodyne radiometry achieves high-resolution spectroscopy by mixing or heterodyning thermal light with laser light. The heterodyne signal is processed with a low-pass filter, bandwidth B, square law power detector, and an integrator averaging time tau to provide a signal proportional to the power within the optical bandwidth 2B about the laser frequency. The full spectral profile can then be reconstructed by scanning the laser frequency. For our system, we use a 100 megahertz low-pass filter, and along with the other RF components, this sets a point spread function shown below, which has a double-sided optical bandwidth of 200 megahertz, a resolving power of 1 million in the 1.5 micron region. That's pretty good for a spectrograph that takes up less than a square foot, or a spectrometer takes up less than a square foot. And that footprint could easily be less if the electronic components were integrated together. There is a trade-off here. We are limited to the information in a single spatial mode. That means we are limited to the power of a single thermal mode given by the Bose-Einstein distribution. Additionally, the single mode limit is only reached when the fiber is spatially mode matched to the thermal source, something that is much easier to do on the sun than other stars. But if those conditions are met, the SNR is given by a simple equation. In comparison to traditional spectrographs, the important difference is that the SNR scales linearly with the number of photons instead of the square root. That linear scaling is nice when you have a coherent state with lots of photons, but a thermal mode from the sun at 1.5 micron has less than 1 photon per second per hertz. So the bandwidth and the averaging time do most of the heavy lifting. Our wavelength calibration is a frequency comb. We integrate this into our system as a second LHR channel. Using the same local oscillator laser, we map out the solar spectrum and the spectrum of the frequency comb. The time domain data is recorded simultaneously on an oscilloscope and looks much like this plot in the upper right. Notice here that the comb line spacing is much smaller than what you'd use on a spectrograph. Here we have only 125 megahertz mode spacing. The calibration procedure involves fitting a Gaussian profile to each line to find its center, and then linearly interpolating a frequency solution between each comb tick. If we send the comb into both LHR channels, that allows us to probe the calibration precision, and that provides an upper bound at the centimeter per second level, which averages down over time. Since we are in a sweeping configuration, only one point is being measured in the spectrum at any one time. We must be careful about slow amplitude fluctuations that could manifest as apparent frequency shifts. To mitigate this, we servo the power of the local oscillator to stabilize the DC output of the photodetector, controlling both the background level and the effective heterodyne gain. Additionally, we have placed the sensitive radiometric components, anything part of the conversion of optical power to voltage, in a thermally isolated box. We still have some coupling to ambient temperature, but on a scan-to-scan basis, the amplitude fluctuations are at the part per 10,000 level relative to the amplitude of the solar signal. And that's equivalent to a noise floor of about 10 centimeters per second per scan. The coupling optics are housed on an autonomous solar tracker, which uses a quadrature sensor for active tracking from sunrise to sunset. As part of a two-stage solar tracking setup, we have an additional piezo-driven mirror for real-time optimization of the coupling into the single mode fiber, and that's in this box attached on the right side. We want full disk integration for sun as a star measurements, and for this we use a flat top beam shaper, which is a refractive device that coherently transforms the Gaussian mode of the fiber into a more uniformly distributed pattern in the far field, seen in green here. This also has the benefit of making us much less sensitive to pointing errors as compared to the Gaussian mode, which can couple in Doppler shifts due to the sun's rotational motion. Although I can't say we're at the centimeter per second level per arc second yet, as we still have some mismatch between the expected and the actual profile that we measure, which has some wings on the edge. Plotted here is an example of the kind of data we get. The particular line we're looking at most is part of the iron spectrum at 1565 nanometers. It was chosen for its high magnetic sensitivity, which is useful for probing solar activity. As seen in a plot of the recorded LHR amplitudes, we were able to take data from sunrise to sunset, or at least until the sun hits the mountains behind Boulder. This data spans 30 gigahertz and is the combination of over 8 hours of data with the color scaled inversely to the local density of points. The curves have been normalized to a continuum level of 1, which changes throughout the day due to air mass. And data with passing clouds has been masked out. The residuals have a Gaussian distribution with an SNR of 40 in a single trace, which cleanly averages up to over 3,000 with 8 hours of data. To analyze line shapes or RVs over these timescales, we had to tackle the issue of telluric contamination. While the 1.5 micron region is considered an atmospheric window, it's hard to truly get away from water, especially at high air mass. We fit the telluric spectrum to a few layer HYTRAN model that allows us to control or fit temperature, pressure, and water mixing ratios. We currently only fit once using high air mass data from early morning exposures and scale that throughout the rest of the day. And we also mask out the strong solar line to emphasize the telluric information in the fit. By perturbing our fits to the telluric model, we estimate that the residual telluric contamination contributes a drift of about 3 centimeters per second in a 3-hour window. The uncorrected radial velocities precision of this data set is about 15 meters per second in 5 seconds and hits a noise floor of 1.5 meters per second at around 1,000 seconds. The telluric corrected version reaches down to about 1 meter per second. However, there's still a complicating factor that we have not accounted for, and that's the air mass induced changes to the solar amplitude. The plots on the bottom actually only include data from the top 10% of the LHR amplitudes. But even in this region, you can see by eye that the amplitude has some curvature to it. We implemented a continuum correction that tries to account for the changes in the solar magnitude that can occur within individual traces, slope in the continuum due to changing power levels. And with that correction, we can break past the meter per second level on a single line, hitting a floor of about 80 centimeters per second. Those are encouraging results, but it can be difficult to diagnose and test for systematics at these levels and iterate the experiment when you need days of data to tell if you've made an improvement. So how can we get to the highest precision in the shortest time possible? One way is to focus our averaging time on the spectral regions with the greatest information content. Because we don't have enough bandwidth to measure the telluric lines in this case, this test was restricted to the low air mass time around noon. What this shows is that starting from a lower point, 10 meters per second instead of 15, we can indeed get down to the 1 meter per second level in a shorter time period and without any other correction. If we further restrict the time series to just a region with a flatter trend line, we see that the signal to noise ratio of this data can even support precision down to 60 centimeters per second. This slide is a little more speculative, but if we were to push that further, what would the results be of narrowing down to only 2 points? RV information is maximized at the steepest points on a line, and using simple derivative sensitivity arguments, we can further maximize the precision by increasing the optical bandwidth to that of the line width. Running calculations using the line shapes for this transition estimate that with the signal to noise ratio could ultimately support 1 meter per second precision in only 10 seconds and 10 centimeters per second in only 1,000 seconds, just on a single line. And while this completely discards the line shape information, I think it is still an interesting limit nonetheless. It's similar to how spectroscopy is performed on atomic clocks, which involves dithering a laser and measuring the amplitude on either side of a line. The differential amplitude is used to servo and lock the laser to the center, and with the laser frequency then directly counted and tracked against a comb. So in conclusion, it's exciting to start getting measurements that push below a meter per second. For the near future, we already have components in place to observe 2 lines in parallel. So we should have data on that soon. And we're working to streamline our data collection and processing so we can have more regular cadence and string many days together. I think we still have paths toward higher precision as well. The continuum correction and configuration of the flat top shaper are somewhat preliminary. There's another polarization state that we're not looking at. We could take advantage of the targeted scans or even the dither lock. There's also other directions that we can take this instrumentation. Instead of disk integrated measurements, LHR naturally lends itself to resolved high spatial resolutions, as there are no mode matching issues there, at least in terms of SNR. And in parallel, we've already started looking at greenhouse gases. We actually have a fun measurement that shows we can track terrestrial wind-induced Doppler shifts to the 10 centimeter per second level. So there's still hope we can do the same on the sun. Thanks.
Thank you very much. Questions? I see one over here. We have mic runners, so please wait until you get a microphone. And if we can have our next speaker come up.
Does the image rotate with respect to your optics during the day?
Yes.
So then you can test your ability to integrate over the disk of the sun by looking for, diurnal signals.
Yeah, and that's I think the beam shaper that we have, we've been very careful to make sure that we're as symmetric as possible on that. Certainly the first time we just stuck it on there, there was a big slope, and yes, we saw a big signal like that.
But that's a feature, not a bug.
All right. Do we have any questions online? No. Okay. Any other questions in the room? All right. With that.